Go ahead.
Thank you. I'll certainly try to tell you everything about LISA, but I think we don't have enough time for that. Now, let's raise our eyes to the heavens and look into space, to LISA, which will open the low-frequency gravitational universe for us. And I do have good news for you, because LISA was selected on June 20th of 2017 by the European Space Agency for the L3 launch slot in the future science program of LISA. This is very timely because this comes only 22 years after the first LISA Symposium, which took place at Rutherford Appleton Laboratory in 1996. And many of the people in this picture are still working on the mission. They don't look any different, except they're much more beautiful nowadays. LISA by now is really a mature concept. The first ideas floated around in the 80s, and LISA was finally proposed in response to the call for missions for the M3 concept in 1993. It was then selected as an ESA cornerstone in 1995, and the 3-spacecraft triangular version that we're looking at right now appeared in 1997, and that has been the baseline ever since. There was very intense studies going on over 6 years in a joint mission formulation between 2005 and 2011, which was then interrupted by the dark ages, also known as reformulation. But now we're finally back to the old 3-arm version of LISA as we're used to. LISA will then be launched into passive orbits, and that means if you do it right, the 3 spacecraft configuration will orbit the sun, looking like a rigid body, like a cartwheel, rotating around its center once per year, while in reality each of the 3 satellites is in its own heliocentric orbit, slightly elliptic and slightly inclined against the ecliptic, with the ascending nodes displaced by 120 degrees around the ecliptic, and that makes it look like a rigid body. So this we have been working on for a long time, but we also had to wait a long time. But then came 2015 and 2016, and 2 things happened in those years. One thing we have already seen, that was this year. We made the cover of several magazines, actually 671 journals all over the world had us on the cover page. And now we are so used to it that when the detectors are running, we are seeing black hole mergers every month, that some people are now getting bored and are saying, another black hole. So, but as we know, we are also seeing neutron stars now. But something else that happened was LISA Pathfinder. Here, still seen in the conceptual drawing with the eyes of the artist, LISA Pathfinder testing LISA technology in space. It also has a long history. It was actually first proposed in 1998. And I still remember I was writing the first proposal, and then we thought about how can we call it. Well, ELITE was kind of a neat name, which in reality meant European LISA Technology Satellite. It was then renamed to SMART 2 in the year 2000 with the little word game like "We are SMART 2." And those days, it was a technology demo for LISA and Darwin. Quickly thereafter, Darwin was descoped, and then the whole thing muted into LISA Pathfinder. And then only 17 years later, we were there in the Industrieanlagenbetriebsgesellschaft Integration Hall in Ottobrunn. This picture was taken in September of 2015, and it was the last time that human eyes saw this satellite, because then the whole thing disappeared into that little crate here. Then it was flown to Kourou in French Guiana in South America. That's where the launch site of the European Space Agency is. And what a month that was, because 2 weeks earlier, we had for the first time detected gravitational waves on the ground. And then we were standing there looking at the LISA Pathfinder satellite. I mean, we knew we had detected gravitational waves, but nobody else, and we couldn't tell anybody. And so we were standing there. And then a little later, it happened on December 2nd, which was exactly to the day, 100 years after the publication of Einstein's general relativity in written form, to the day. So no public relations agency could have done this any better. And it was purely accidental. It only happened because the Indians who were in front of us on the launch pad didn't get their satellite up, and so we had a launch delay of a week. And that's what put us exactly on that day. And we launched it, LISA Pathfinder, with a night launch at 1 a.m. This is the original footage from our launch. It's an event you don't forget when you're standing in the jungle. In pitch dark night, 40 degrees, 100% humidity, 100% mosquito saturation in the air. And then you see your thing being launched. Okay, then we went into the most complicated low Earth orbit maneuver that ESA had ever flown, because we needed 6 apogee raising burns to get us out of the gravity of the Earth. And then we were finally in a transfer orbit to the Lagrange point 1, which took about 2 months. There we separated from the propulsion module and went into a wide Lissajous orbit around the Lagrange point 1. This orbit is also known as the potato chip orbit, which you will easily understand when you look at it from the side, because this is an orbit around an unstable Lagrange point. That means it's not in a plane. It really looks like a potato chip around there. You can ask me about many things that happened there. It worked very well, to summarize it. This was the first laser interferometry in space, and it was also the first distance measurement between free-flying test masses in space ever. And here's the only essential thing on LISA Pathfinder: 2 free-floating gold cubes, each one about the size of my fist. And all the rest is just diagnostics and shielding. So there's a little laser interferometer in between you use to measure the spurious forces, and a few vacuum cans. You have the free-floating gold cubes here inside the vacuum cans. In reality, of course, it didn't move that much, but still. And then the satellite with all the electrics and solar arrays, and we made another cover. Again, this magazine, Physical Review letters. Why? Because the mission was so successful that we had built the stillest place in the universe. So if you want to give it in a nutshell, the proof masses were so quiet and the measurement was so sensitive that it would have been a big signal if a virus, not a bacterium, they are large, so a virus had sat down on one of the proof masses with its weight. It would have gone chunk on there. So let's be a bit more quantitative. This is the residual acceleration spectrum. That means the residual deviation from perfect geodetic flight following a curved spacetime. And this here is 1 femtog. That's 15 orders of magnitude less than the gravity in this lecture hall. And here's the spectrum: 1 hour, 1 minute, and 1 second. This here is the requirement. This is the requirement for the full LISA mission in terms of residual noise force. And this is the requirement for the LISA Pathfinder mission. As usual for a technology demonstrator, the requirement for the demonstrator is relaxed by about a factor of 10 relative to the main mission, because engineering wisdom has it that for a well-understood system, you can safely extrapolate by about an order of magnitude. And that's why you relax, to make it a little less expensive and a little less difficult. And then it happened. It was March 1st. It was the first day that we scientists took control over the satellite. We operated it straight out of the box as industry had built it. So there was no optimization, no tweaking, no nothing. Dead reckoning, just turning it on out of the box. And this is maybe the most important realization of the whole mission, that industry can do this. Just following specifications, just screwing it together, because this is what we got. And you see that with dead reckoning, with no optimization, it was way better than all the requirements that we had for the technology demonstrator. We could have gone home on that day because it was all done. But physicists don't go home. They get greedy. And so we started tweaking. And 2 months later, this is where we were. We had for the first time reached the specifications for the full LISA mission. But not just this. We also started understanding why we got what we got. And here we see a noise diagram that shows many of the important noise sources. You see things like here, OMS sensing, that's the phase noise of the laser interferometer in there. You see down here things like gas damping, you see laser radiation pressure, Stray voltage fluctuations, it's all down here. But over most of the frequency range here, you see something that's called gas damping. What's that? That's the noise due to the Brownian molecular motion of the residual gas inside the satellite. And that was as it was because we had opened the system 62 days after launch to the vacuum of free space. And we could see the residual noise here in the low frequency range from 3 to 8 millihertz drop like a perfect 1/t, where t is the time thing. Here, you see the low frequency noise going down and down. Why? Because the satellite was outgassing. It was outgassing into free space. This is the behavior of a typical unbaked water-dominated vacuum system, outgassing into space. And here, 190 days after launch, we were crossing the LISA requirements for the full mission for the first time. But then it went on. And finally, in February of 2017, this is where we ended up. And you see, finally, we reached a residual noise performance, which is a factor of more than 2, better than required for the full LISA mission at all frequencies. And also all the way down to 20 microhertz here, a low frequency never ever reached before. And it's utterly impossible to do this on the ground. And even in space, it's a pain to get to these low frequencies. Just imagine what this means. 10 to the minus 4 hertz means one oscillation is 10,000 seconds. In order to measure anything, you need a few oscillations. So that means a few days. And in order to average the periodograms a few times to get a decent noise curve, it means one data point is 2 weeks. You can't do much at these low frequencies in a limited lifetime. Anyway, if you want to summarize it, you could say LISA works. And ESA has reacted to this and has anticipated the selection schedule of the large missions by 4 years. The call for mission concepts for the large mission L3 came out in 2016, 4 years earlier than originally anticipated. And the best thing is, NASA is finally back in LISA with a couple $100 million. The scientific community responded to the call for mission concepts with this beautiful document, which you can still download from the website. It was submitted by the LISA Consortium of 12 European member states plus the US. And it's really a beautiful document. Not only does it have beautiful colors on the cover, but it also has 42 pages, just for the insiders among you who know what that means, that 42 is the answer. What was it that we proposed? We proposed 3 arms of the interferometer of 2.5 million kilometers each. You can ask why 2.5 million. It's non-trivial, the answer. We're using 2-watt lasers, all technology which is there, flying actually. We're using 30-centimeter telescopes, and that makes the whole constellation breathe by about 1 degree per year. And that makes the arms breathe by a Doppler shift of about 5 megahertz. The whole thing can be launched on a single dedicated Ariane 6.4 launch into direct escape hyperbola from the Earth, and then it goes once around the Sun, slightly wider than the Earth orbit, and that means when it crosses the Earth orbit again, it's about 20-30 million kilometers behind the Earth. Then you stop it there and go into operational orbit. That was selected by 20th of June by the SPC of ESA. But even before that, ESA had started the phase 0 study because everybody knew it was going to be selected. So already in March, the phase 0 so-called CDF study started, meaning concurrent design facility. That's a room full of engineers who design the mission in real time, at the same time, everything. As a result, we think we have a feasible technical baseline now for LISA, with a transfer of 15 months, and we're designing for 4 years of guaranteed operation with an extended mission lifetime of 10 years. We're using electric propulsion for the orbit transfer, cold gas for the micropropulsion on orbit. The payload is pretty much what it always looked like, and we still have a healthy mass margin and need about 2.5 kilowatts of there. The only downside is it's no longer round, it's square now, and so it has earned its name, the coffin. but I'm confident that in the following phase A study, we'll make it round again. As I said, it's going to be launched into a direct escape hyperbola, separated immediately, and then each one of these goes with their own propulsion module into the orbit around there. A few technical details which you might want to pass on. We need governance. Now that the phase 0 is concluded and kickoff for phase A is happening in a few weeks, we must have a new governance structure in there, and it grew out of a lot of background and face-to-face discussion. And as the history of the LISA team has it, this is a very consensus-oriented process that we use there. First, we reach agreement, and then we make it formal in there. But we do have formal documents. Also, it'll all go public within the next few weeks, all these documents. There is a well-sorted management plan, which you can see is already in revision 4 up here. There's a complicated structure, everything you need for a real space mission. It has a top layer, which is the agencies, where you see that it's an ESA-led mission with NASA as a big but smaller partner. It now has an appointed science team, and it has a very strong central system engineering office sitting inside here. It has a consortium layer, which is, as scientists, providing a lot of the hardware and a lot of the needed software and science studies, but it also has a bottom layer, which is a community layer, which consists of working groups that are led from inside the consortium, but they're reaching out into the wide community. Some of those working group members are in the consortium. That means they have deliverables to the project. But many others are just scientists who are interested in contributing towards this in the wider community. Please pass the news, become a member of the consortium and of the working groups. This is a formal process based on commitment. So if you want to be a real consortium member, you have to deliver something to the project. It can be hardware, but it can also be software, data analysis, or a coordination role. This is all specified in a memorandum of understanding. It's a yearly reporting and review, and it's screened by an application board, and there's appeals process. The whole thing is described in this document, which you can find on the web in there. Just go on the web. It's an easy interface, explanations, explanatory documents, and then you just upload your application to this. The process is running as we talk. As of April 19th, we have received 123 group applications to be a part of the LISA team for a total of 747 members who have now applied to become members. But probably as I'm talking, it's already approaching 1,000. This is a very promising process because in the old Proto Consortium, we only had 345. But these are all real because they're promising real work that they want to do. All the technical details you can find also on the web in the design description document, which will go public within 2 weeks or so. And this is what we are working towards. These are the LISA science requirements. And you see, this is a sensitivity curve. Here's the millihertz range. And all these colorful bars here, those are the limiting science objectives that we are looking at. I don't want to talk about all of these, so they're all identified in here. If you go into the science requirements document, and you see them all explained in great detail. I just want to say that most of the LISA sources are way above this limiting sensitivity curve here. Those are the borderline cases that we want to get to. So don't get worried if they're all close to the sensitivity curve here, because most of the sources are here, way above all of this. And the best thing is, this sensitivity curve is not something we just require. We know we can get it, because here it is, and we have already done much better than that. LISA works, and LISA Pathfinder has shown that it does. All we need to do is make the arms 2.5 million kilometers instead of 38 centimeters. But there's really nothing happening in between except for Maxwell's equations, and those we can solve. Let me talk a little bit about the science to close with. Science by 2030. We will have wonderful new observatories by that time. And as you can see, I'm including the LHC here under observatories. because a lot of the science questions that Lisa will address are in the realm of particle physics. But there will also be electromagnetic telescopes, the very large telescope, the extremely large telescope, and the overwhelmingly large telescope will all be out there observing, and even the James Webb Space Telescope will probably have left the ground by that time. But I dare to say that many of the science questions we will be looking at in the 2030s are already known. We will still look at cosmic structure formation and black hole growth. We will be dealing with physics beyond the Higgs. We will look at phase transitions on the TeV scale. We will be studying cosmic strings, dark matter, and we will still not have understood the physics of dark energy. Lisa will address all of these, and I will not talk about all these science questions, just about two which are close to my heart. One is black holes. And this is the parameter space of black hole astronomy as it will be known in the 2030s. Here is the mass. Here's 1,000 solar masses, 1,000,000 and 1,000,000,000 solar masses. And here is the distance in redshift. So here is 0, here and now in this lecture hall. Here is reionization somewhere here, and there are the dark ages. Now the beautiful new telescopes that we'll have, they will be looking at the high end of the mass range of black holes, roughly out to reionization. The gravitational wave telescopes, Advanced LIGO, Advanced Virgo, and CAGRA, will be looking at the low end of the mass range, a few hundred solar masses, out to redshifts of maybe 2. If Einstein Telescope and Cosmic Explorer will be observing by that time, they will go to slightly higher masses, to a few thousand, and out to about reionization. But as you can see, most of the parameter space of black holes will be completely uncovered, even by the 2030s. And now you can guess where Lisa might be sensitive in this diagram. Well, where could it be? Yeah, right there. It will observe with almost ridiculous signal-to-noise ratio out to almost arbitrary redshifts anything that is there, if there is anything. And these will be very high signal-to-noise ratio observations. Here I've plotted a weak signal for you. It's a merger of 200,000 solar mass black holes at a redshift of 5. And I've plotted this over the instrumental noise. And this is not guessed instrumental noise. It's the measured instrumental noise from LISA Pathfinder in red. And if you say, well, there's no noise, almost. So let's zoom in. See, there is a little bit of noise. This is what I call high signal-to-noise ratio observations. A few more things on the side. Many people don't realize that LISA will be very sensitive towards dark matter. If there is a dark matter spike around black holes, as many people expect, then this dark matter spike will influence the phase of an inspiraling object that falls into the black hole. And it will lead to a very sensitive probe of this. And the best thing is this will be sensitive to dark matter, even if it interacts only gravitationally, because it is gravity, after all, that we're using to observe this. We can also do cosmology with standard sirens, because inspiraling compact objects are the equivalent to standard candles for optical astronomy, but they're standard sirens from first principles. Because there's no calibration required. Just by looking at the signal shape, you know the absolute luminosity of the source. And then you compare it to the apparent luminosity, and you get immediately from first principles the luminosity distance. So without any electromagnetic counterparts, within a few months, you get the Hubble constant to fractions of a %. And again, without any electromagnetic counterparts from gravitational waves alone, without a year or so, you get the dark energy equation of state parameter to a few %, which compares very favorably to dedicated missions, which are designed to do nothing else than dark energy. With all these sources like massive black holes, extreme mass ratio inspirals, and LIGO-type binary black holes, LISA will be a very sensitive cosmology probe, giving us the luminosity distance to redshift relation over orders of magnitude in redshift, over a very wide parameter range. It's time to get prepared to analyze the data. This is being done by mock data challenges. One was active until 2010. Please. There's an in-spiral coming in. Yeah, there was a high eccentricity one, as you could hear easily. We are resurrecting this now. It's going on. So it's a project-oriented LISA data challenge. The web page is open for anybody. Just go there if you're interested. Download data. The first data release is out there. This is pretty much what it looks like. Ask me about it if you want to know more. And to close, I want to point out that had LISA been up there 10 years ago, we would have detected those LIGO black holes 10 years ago. Because this is where LIGO is, and there in black is the very first event, 150914. And you see, here at 30 Hertz, it enters into the LIGO band, and here it exits. But 10 years ago, 10 years earlier, these two black holes were far apart, that far apart, and circling each other smack in the middle of the LISA band. Not only would we have detected them, but we could have predicted the time of merger to a second and the place on the sky to a fraction of a square degree. And I can guarantee you that any big piece of glass on this planet would have looked in that direction during that second to see if there wasn't really some trace of an electromagnetic signal. So that's where we are. The decision on the L3 adoption will be in 21, the first large launch in 28, the second one in 34. But an intriguing idea that is gaining momentum right now is that really with Athena, the nominal L2 candidate, bringing in delays, and LISA being much more ready than anybody ever thought, the current thinking inside ESA is that it would be desirable to really launch a big X-ray telescope and a gravitational wave observer in the low frequency range together and operate them simultaneously. And that would really be a fantastic achievement because LISA could tell the X-ray people, look there, you're going to see something. And it's about time we do this because I want to hear the Big Bang in gravitational waves, and I will soon. Thank you.
So now that you've had this great success with the Pathfinder and the launch is imminent, what are your thoughts on the next generation beyond LISA? What might that look like? Is it longer baselines? Is it, how do you do something next?
Thank you for this question. This is really the most burning question in my mind. What is the LISA follow-on mission? So we have many ideas. So I think Matt has outlined many of the design principles that you can do. You can do more of the same, just bigger and better, or you can think of different technologies. I would say give us a few years to do the basic stuff in the lab. And I mean, the best known follow-on concept is the Big Bang Explorer, which is a prime example of do the same, just bigger and better and more of it. But there may be other alternatives, and it will also depend on the science. For example, there is a window in between the ground-based instruments and the space-based instrument LISA at medium frequencies of a fraction of a hertz to a hertz. It may well be that the next space mission will target that frequency range. It'll depend a little bit on the science that we find with Cosmic Explorer and LISA. So the verdict is not on the table yet.
Charles. So with your great sensitivity, do you have to worry about confusion of sources, one with the other?
Well, that's an abundance of riches. It's a problem we'd like to have, right? Too many sources. And yes, there will be a confusion background, but it's not a noise background. It's real signal. It's like optical astronomy at daytime. The sky is always bright. But you can see the full moon, you can see the planets. It's up to you to dig into this signal background, and that's something that's being practiced right now. At the low frequencies, you're going to be limited by a confusion background of galactic and extragalactic binaries. But of course, the longer the mission lasts, and the better your resolution, the deeper you can dig into that. And in principle, it is even possible to dig completely through this background by identifying every single binary system in the universe. The number is finite, as we know. universe has a finite age, so in principle you can get them all. But that's something really for the future. So for right now, we are satisfied just getting down to the signal background. That is, by the way, the reason the arms are 2.5 million kilometers and not 20 million kilometers, because making them 20 million kilometers would shift the whole sensitivity curve towards lower frequencies, and there is no point, because at the low frequencies you have this background from the binary systems in the universe. So that's a result of a careful optimization.
Erwin, just because.
Fascinating talk. I wish I would be around above ground to see what happens in 2000.
Oh, I think you will.
Anyway, my question is more historical, going back to the beginning of LISA. You seem to say it started in the 90s, but I can swear I remember hearing about it from Peter Bender either in the
80s.
Early or middle or late 1970s. So this has a longer history than I think you allowed for.
Yes, yeah. I was referring to the LISA mission proper. The first idea is to launch a space interferometer came about a few, I would say, days or years after the first ideas floated to detect gravitational waves with laser interferometers. I mean, it's a kind of obvious thing. Once you have realized that you can detect gravitational waves with a laser interferometer, and once you've realized that bigger is better, then it's an obvious idea to go out into space. The first real studies were done in the 80s. And again, it was Peter Bender who kept this floating for many, many years. And he's still there driving us forward, making this work. So that was in the 80s, and the very first ones were, well, seen from today, kind of naive. So there was a kilometer-sized rigid structure made from steel that was studied at some point. But also in the 80s, there was an early idea of flying a free-floating laser interferometer. It was called Lagos in those days. But LISA proper really appeared in response to the ESA M3 call for proposals. I know very well because we put it together in 1992, in late 1992, in the Chilean Andes, because the baggage handlers were on strike, and we were stuck in the mountains at a conference resort. There was what do I remember, GR11 or something. And what do scientists do when they're stuck in a mountain resort? They come up with a new proposal. And that's where the first LISA proposal was conceived. It was in the fall of 1992, with Pete.
Last quick question by Matt. Yeah.
Hi, thanks. I was wondering if you could say something about your last slide here for detecting the Big Bang. It seems like the stochastic background is still out of reach. Could you say something about that?
That depends on what happened in the early universe. So now let's be exact. When I say Big Bang, of course, it means the early universe, something from the early universe. Nobody knows what the Big Bang was, and we can't describe it. So if really the only thing that happened in the early universe was slow roll inflation, then we can't get it. Not with LISA. That's a few orders of magnitude out of reach to get to the background of slow roll inflation. But pretty much about everything else that people are studying about the early universe gives you signals which are orders of magnitude larger than this, no matter what it is. Phase transitions, kinks, cusps, cosmological defects, brains, all of these give signals which are much stronger and which could be detectable by LISA if they exist. So it's discovery space. We don't know what we'll get. If it is there, we'll get it.
And a half-a-minute quick announcement, but relevant to LISA by Fred.
I thought Karsten was going to say it, but he mentioned the very first LISA Symposium some 20 plus years ago. This has gone on every other year, alternating between Europe and the US. And the next one is in Chicago this summer, in the middle of July, in a beautiful location downtown. And the abstract submission and registration deadline is today.
That reminds me, I have submitted my abstract last night. Let me also announce that the next time the LISA interferometry is going to fly in space is going to be in a week, because on 19th we have the launch of Grace follow-on from Vandenberg Air Force Base. And Gray's follow-on will be the first intersatellite laser interferometry. And it will use LISA technology to measure the gravity field of the Earth. So cross fingers that everything works.
So let's thank all our 3 speakers before the break.